Worksheet 5C, column buckling. 20-foot long column make of A36 steel. So from that we have L, the length of this column is 20 feet. A36 steel, which is we have sigma yield equal to, if you don't recall, go to appendix B, 36 KSI, and we also know E for the steel equal to 29,000 KSI. So that is appendix B. And then the support, to support a 125 kips actual compressive load. So that basically the P actual equal to 125 kips. Determine the most economical wide flange beam. So that, as you can see, the question at determine the most economical wide flange beam, and for that one basically we determine the size of the structural member. So basically this problem is a design problem. Failure is defined as buckling or yielding. So both, we have to consider both. Use the factor of safety with regard to buckling is 2, and the factor of safety with respect to yielding is 1.5. And consider the column is pinned in all directions at both ends. So from that, as you can see, this problem is similar to worksheet 5A, part A, that they both ends in all directions are the same. So we need in the Euler buckling equation or the critical load, the I, the area moment of inertia, we need to get the smallest I among the I go through the neutral axis of the cross section, smallest I, smallest area moment of inertia. So from that, let's start to this problem model with the column. So that is the column and pin as both ends. So we have the pins and pins, 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 and then we have a load P actual, P 125 kips, 125 kips, and the length of this one is the length is 20 feet, which is 20 times 12, so it will 240 inches. So that's what all we have in here. So let's get some information just mentioned earlier. So this problem is pin in both ends in all directions. So we have K, the effective length factor, equal to 1. And as mentioned earlier, we have it A36 steel for the material. So from that we have sigma yielding stress equal to 36 KSI, and E Young modulus equal to 29,000 KSI. And if you don't know, go to appendix B in the textbook. Appendix B in the textbook. And then they give you the factor of safety with regard to yielding is 1.5, and the factor of safety with regard to buckling equal to 2. So from that we can consider both buckling and yielding. So let's start with the first one, due to yielding or crossing. Yielding or crossing. So from that we have the general design equation, as you can see, the actual less than or equal to allowable. In this case, the yield, as you can see, we know the yield stress. So we the level in here, actual and lower level, determined as a normal stress. So what does that mean? We have sigma actual less than sigma allowable. And sigma actual is equal to, for the normal stress, is P over A. So now we have that is P over A less than or equal to sigma allowable, the yield due to yielding. So the failure level is the yielding stress divided by the factor of safety. Because the factor of safety equal to the failure level divided by the allowable level. So allowable level equal to the failure divided by the factor of safety. In that case, it's about the yield. Factor of safety due to yield. So from that, we can plug in what we have in that equation. P, actual load, 25 KSI, divided by area, which we don't know yet. We want to determine the cross-sectional areas. In this case, so 36 KSI divided by yielding factor of safety 1.5. From that, we have A have to be greater than or equal to 5.21 inch square. So for yielding, we need to have cross-sectional area of this Y flange shape at least 5.21 inch square. That is for yielding or crossing. Now, if we go to buckling, what do we need about the cross-sectional areas for this member? So, you have the same design equation, general design equation, the actual less than or equal to allowable, exactly the same. And now, because the buckling, the failure is determined by critical load P critical. So from that, we can, instead of the sigma that given, we already be able to find out the critical load that make the member to buckle. So from here, we the level that we are talking about is the load. So P actual less than or equal to P allowable. And P actual, we already have 125 kips. It had to be less than the P failure over factor of safety, P fail over factor of safety due to buckling. And for buckling, as you can see, P fail equal to P critical divided by the factor of safety due to buckle. So from that, we can plug the critical equation. So 125 less than or equal to P critical equal to pi square EI over KL square and time the factor of safety as we divide that one. Factor of safety due to buckling. So we can plug in 125 less than or equal to pi square E 29,000 KSI. I, we don't know. That is the one characteristic geometrical properties of the cross-sectional areas, or cross-section of the members. Divided by K, and you can see K for pins, it's 1, so that will be 1 here. The length of this column 20 feet, so it is 240 inches square times the factor of safety, which is for buckling 2. Factor of safety is 2. So from that we can only one unknown is I. So what does that mean? I have to be greater than or equal to 50.3 inch 4. So that the requirement for cross-sectional of the member of the column. The areas due to yielding have to be at least 5.21 inch square. The area moment of inertia of that cross-section have to be greater than or equal to 50.3 inch 4. So we need to find out the Y flange shape. The Y flange shape that meet both requirements. So how to find out the Y flange shape? We need to go to appendix C. So before that, I need to specify here before I go to the Y flange shape. Appendix C to compare the requirement. What are the requirements we are talking about here? So the requirement here is the cross-sectional areas have at least 21 inch square, and the area moment of inertia at the weakest axis had to be at least 50.3 inch power 4. That's the requirement. Okay, so that compare the requirement to wide flange beam properties. And that where that we can find is in appendix C of your textbook. Okay, appendix C in textbook and available on Canvas. Okay, so right here we let me go to orient appendix C, and then we get the answer for this problem. So this is appendix B, and now go down to appendix C. And similar to appendix B, they have both SI unit and US customary unit. So let's go to here, start of appendix C, properties of raw steel shapes, and Y flange stand for W shape, right? So start of the symbol of the Y flange, as you can see here. So it W36 cross time 300. So how can we read that number for each? So let me give one example here. For example, the first one, W36 times 30. So the W stand for Y flange, right? Y flange 36. It stand for the nominal depth or the height of the cross section. Nominal depth or height of cross section. And the 300 here is the weight per linear foot. The weight of the beam per linear foot. So for example, W36 time cross 30. 300. What does that mean? That is the nominal depth is 36 inches. Nominal depth inches. And then the 300 is mean the weight per linear foot. In this case, for example, that example there is 300 pounds per foot. for that section, and similar for others. Now there are many properties that you have for that cross section. The areas 88.3 square inch, the depth, the third column, that is the actual depth. So it's about 36, but it's not exactly the same. They have the width of the flange. What is flange? As you can see, that will be the flange, and that is the web. Okay, so give it the flange, the width, BF, thickness, TF of the flange, and then the thickness of the web. They also given for axis, XX and YY. How they define the XX is parallel to the flange, perpendicular to the web. That is the axis X that they define. And then the Y-axis also go, basically that is the neutral axis, go through the centroid that parallel to the web or perpendicular to the flange. And as you can see, for all cross section, the IX, for example, the one that 36 by 300, you have it IX equal to 20,300 inch 4. Why the IY? It's only 1,300 inch 4. What does that mean? For this cross section, the area moment of inertia about y-axis is very small compared to the x-axis. And width applied to the column, if we use that for the column, this column tend to be buckled around about y-axis, not x-axis. Because if you see the critical load in Euler buckling equation, it's proportional to the area moment of inertia. So that's why it buckle about the y-axis. And if not, you go back to my demonstration in the worksheet 5A, in part 1. In that worksheet 5A, you see the demonstration, why it buckle in the weak areas with that demonstration. So that when you find out the I, we're just looking at the IY because that's smallest and it needs to be sustained with the buckle. So you select the weakest axis that have to be buckled. Okay, so with that, we go ahead to find out what are the areas, what are the cross-sectional area that have area at least 2.21 inch square and the I at least 50.3 inch 4. So go back to the reference. Let me go down, give you a few, and of course it takes time. Because we design, it takes time. I give you one example here. Go to that appendix. The first one that I'm looking at is the one 14. So 14 by 53. 14 by 53. I have the area, the second column, and you can see the areas is 15.6, which is greater than 5.21 inch square. And the I, in this case, 57.7. Drop that down. We will write down later. And then the second, can go ahead. This is SI unit. You have to skip that page. Go back to the US customary units. W12, which is the actual depth is 12. If we look at the 50 by 50 pound, we have the area 14.7, which is greater than 5.21, and IY is 56.3, and as you can see, IX is 394. So it always look at the IY, get the smallest. If the end condition for both direction, all direction are the same. So look at the weak point. If the end condition, the support condition are not the same for two directions, so you go back to the example in problem 5A part B. 5A part B, so that you can know how to deal with that. And then we can also go to the W10 cross 45. And then we have area 13.3, also greater than 5.21, and the area moment of inertia about y-axis 53.4, also greater than 50.3 requirement for yes. And the last one I'm going to deal with is 48, the area 14.1, greater than 5.21, and the area moment of inertia is 60.9, which is greater than 50.3 inch 4. And we cannot go more economical. For example, W8 by 40, W8 by 40, and you can see the area emit 11.7, which is greater than 5.21 inch square, but the area moment of inertia is only 49.1. We need at least 50.3. So that's why we don't go down further in that area. So those are the 4 possible candidates that we can use for this design. First is 53. So that one is W14 by 53. The second one is W12 by 50, W10 by 45, and W8 by 48. So with that, we can go back to here and we can write out the possible acceptable choice. Possible acceptable. And then it takes time. You need to go one by one line to see that why I choose that. You know, if you do design, you need to take some time. But here, because the video I one shot, I already picked, so I go to hit to the point immediately. So the possible choice, and you can see the first one is the W14 by 53, and with that I have the areas of that one is 15.6 in square, and then I have IY for that one equal to 57 by 7 in 4. And if I use W12 by 50, the areas, it will be 14 by 7 inch square, and the IY for that cross section is 56.3 inch 4, and W10 cross 45, the areas equal to 13.3 inch square, and the area moment of inertia about y-axis equal to 53.4 inch 4. And the last one that we just discussed using appendix C is W8 cross 48 by 48, the areas equal to 14.1 inch square, and the IY equal to 60.9 inch 4. So all of this, and you can see the area greater than 5.21, and the I is greater than 50.3 inch 4. That are the requirements we need. And since that are the possible candidates, so with that, which one we are going to choose the best? We choose the best, and the question asks is the most economical Y flange. So it means that we want to pay the less. When to pay less, it means it have to be less weight. So from here, as you can see, all of this, the last number on that W14 by 53, etc. The last number 53 stands for the weight per linear foot. So with that, we choose the cross section with the less weight. So you will pay less. So from that one, you will choose that is the best candidate, right? So best or most, we can say best, most economical white flange shape here is W 10 by 45. Okay, so that should be your final answer there. Make sense? So now this example, we know how to design with both yielding and buckling, and it also how to read and get the information from appendices for Y flange shape to get the design, the requirement for both yielding and buckling.